What's going on, everyone? You're back with your boy Jono for another quick math lesson. Today we're going to look at something called conditional probability. And this is where you know something for sure going into an experiment or a chance situation. And this will change the likelihood of something happening based on the information that you've already got. So a really classic example of this is cards. You know what's in your hand, right? So there's no way that the other person could play the card that you've got. So you know that that outcome has now changed. The probability of something occurring is different because of what you can already see. And this is a really important thing for our probability in real life. Being able to take in information and then predict the future based on some outcomes that have already happened is essential for probability to be a useful skill in real life. So the language that we use for conditional probability is we use the term given. And the symbol for this is just a straight up and down line in between two pieces of information. So the way that I like to think of given is it said, hey, this has happened. We know for sure this has happened. So now what's the probability? Because of this thing we know, how does that change the percentage chance that something might happen? So you are going to see it written down as PR, or the probability of A given B. So what that means for this one is, hey, what's the probability of this event A happening, knowing that this event B has already happened? The big thing that we do need to notice is that the sample space is going to change almost every single time because we know that something has already happened. So it means that all options might not be possible anymore. Again, if we're thinking about cards, if you've got a red 7 in your hand, there's now 51 possible outcomes, not 52, that could happen because you already know for sure one thing's already off the table. So these questions start really easy. And that's great because it allows us to be kind of intuitive with these questions. So what's the probability of rolling a 4 if I know for sure it's not going to be a 2? So this is really easy. So based on what we talked about before with the A and B, A is what we want to happen. This is the event we are looking for. So the event A is, hey, I want to get a 4. And so that's our event. And this can only happen in one way. We can only get a 4. And then for B, we know the condition. Hey, it's definitely not going to be a 2. So all we need to know is that instead of there being 6 options for this one, there are actually only 5. So my probability is the outcome I want, 4, there's one of those, divided by the possible outcomes, not 6, but 5, because I know for sure that a 2 can't be rolled. So my answer for this is just 1 over 5. Happy days. Very easy maths. Just reading the question is the hardest part of that problem. So pro tip, the sample space is what's changing. Please make sure that you're not taking every single thing that could happen, right? Reading the question, the sample space options will probably reduce. And this is where the maths kind of comes in. The math stays the same. What we want divided by what could happen, but what could happen has changed based on the information we already know. So the easiest way to come up with a formula for this conditional probability is to have a look at this Venn diagram. So in this example, I've got people that do athletics at school and people that do basketball at school. And again, in that middle section is going to be your intersection A with the little n, B. These are the people that do both. So in this situation, as a teacher, I'm trying to find notes or something to give to students that are doing athletics, and I rock up to basketball training, okay? The only people there are people that play basketball, right? No one else is going to be there jacking up shots, right? The coach has got the basketball team there. And I want to know, hey, out of you guys, who also does athletics? So now I'm not looking at the whole year group, okay? The sample space has changed. I'm only looking for people that do athletics who also play basketball or out of the basketball team. So if we were going to put numbers on this, let's say that I had 12 people only doing athletics. I've got 7 people that do athletics and basketball, 14 people that play basketball only, and 6 that do neither. So if I'm at basketball training, just think about it. There's only going to be 21 people in the gym at that time. They're the only people that I'm now sampling from. And I want to know how many of these guys do athletics. So that means it's the 7 people out of the total basketball players, which is 21. So my fraction is just 7 over 21. And that equals a third. And that's all the maths that we've got to do, right? It makes sense when you really think about it before you start getting into the maths. If I ignore these people, the sample size has to change. I'm not talking about everyone else. I'm only talking about one subset of the whole group. And this is how we get to the formula. It's the intersection, or the A and B, divided by B, or given the new sample space. Hey, what's the chance that I get someone from a different group? So this A intersection B divided by B is where we're going to get all of our marks. What I highly recommend is just when you start these questions, write out what A is, write out what B is, and you will get answers 100% correct. So for this one, we're looking for the probability of picking a student that does music who also does woodwork, or given that they do woodwork. So for this, we've just got to write down our A and B in order to see exactly what we're looking for. So we are looking for a student that does music. So A is music. That's the event we want. But the B is they have to do woodwork. So B is going to be our woodwork. So we are looking for a student that does music and woodwork. So M with the N, woodwork, divided by all the people that do woodwork. And that's how we're going to get to our answer. So this is nice and cruisy off the table. There's only 29 people that do woodwork in total. And of those 29 students, 21 of them are doing music as well. So that means that my answer is just, hey, the people that are doing both, 21, divided by the people that do woodwork, 29. 21 divided by 29 doesn't simplify. That's your final answer. This conditional probability does really help out when we're talking about large scale kind of data distribution, because it really helps narrow in the focus for what we're trying to look at. So for this example, we're looking at gambling in Australia. So 28% of adults in Australia do gamble, which is a pretty huge number. But people would be like, this is all right. Only 1.7% of Australians are gambling addicts. So it is a big deal, but it's not a massive part of the population. So is it really doing too much harm? But there is a massive problem with this. The gambling addicts are only going to be people that do gamble. So they've been accounted for twice in our population survey. So what a better question is, hey, if you gamble, what is the chance that you are going to become a gambling addict? So the sample space has changed. We're not looking at 100% of Australia's population. We are just looking at the 28% of people that already gamble. So this changes the entire equation. So we've got to assign our notation for this. A is the people that we're looking for. These are the gambling addicts. B is the entire population that does gamble. So we're looking for A intersection B divided by B. So A is the 1.7% of Australians that are gambling addicts. This is divided by the 28% of Australians that gamble in total. And this is actually equal to 6%. So there is a much higher chance for you to become a gambling addict if you already gamble. So the 1.7% is a little bit misleading, right? Not everybody has 1.7% chance of becoming a gambling addict. Only if you gamble do you have a higher percentage of becoming someone that has a problem with gambling. So this is a little bit of nuance to these big overall probability stats that is really important to think about when you're listening to arguments made by politicians or media as you go through life. Being able to say like, I don't think we need to use the entire population for this kind of probability or this data. We could just use a subset of the population to try and really find out, hey, what are the chances of something occurring? Thanks so much for watching this lesson, and I'll see you later.